In lecture 3, we're going to do a quick summary of chemistry of ethers, epoxides, and sulfides. This lecture is actually going to be mostly review. We've done a lot of chemistry involving ethers and epoxides so far, basically from our substitution chapters and our alkene chapters. We're also going to add sulfides to this, but sulfides are a lot like ethers and epoxides. So there's not a whole lot of new information here. So this is mostly review, and that's okay. It's just going to be a quick lecture before we wrap things up and move on to spectroscopy. So ethers are the functional group that contain a carbon bound to an oxygen bound to a carbon. So an ROR functionality. Those R groups can be identical or they can be different. So R and R prime could be different, but they could be the same, R and R. They're kind of related to alcohols. You can maybe think of an alcohol being halfway between water, which is HOH, and an ether, which is ROR. The alcohol is ROH. So a lot of chemistry that water does, with oxygen being nucleophilic, or an alcohol does, again with oxygen being nucleophilic, is the same with an ether. The ether oxygen can be nucleophilic. So here are some examples of ethers. This is called diethyl ether. We're going to do naming in a few slides. You can see why it would be called diethyl ether, because it's an ether with both of the R groups being ethyls. This is methyl phenyl ether, again, where one of the substituents is a methyl, the other is a phenyl group. This is, of course, unsymmetrical. This is called tetrahydrofuran. This is a cyclic ether. It's a 5-membered ring where we've got 2 R groups on the oxygens. This R group on the left side of the ring and the R group on the right side of the ring are actually symmetrical. This is a symmetrical cyclic ether. So ethers are polar and they are aprotic. There are no acidic hydrogens. Alcohol and water, of course, have acidic hydrogens, but the ether does not. So these are very common organic solvents. They are good for reactions like SN2 or E2. They're also used in Grignard and lithium reagents to make them using the solvent. We use a ether as the solvent. So these are common organic solvents. They are not hydrogen bonding because there are no acidic hydrogens. So they tend to have very low boiling points, usually from, say, negative 25 degrees Celsius to 35 degrees Celsius. They are tetrahedral for the most part. The oxygen certainly is tetrahedral. It has the 2 R groups and the 2 lone pairs, so it's sp3 hybridized. They've got that geometry. They are often used to stabilize strong Lewis bases. We saw that, for example, with BH3THF. THF stands for tetrahydrofuran. The boron complexes with the lone pair on the oxygen to stabilize the boron and prevent the borons from dimerizing and polymerizing with each other. Ethers have played a pretty important role in the history of modern chemistry. A scientist named Charles Peterson was working for DuPont in 1967, and he discovered, or I guess you could say, he invented what are called crown ethers. These molecules on top here are crown ethers. They are large cyclic structures that have repeating ether patterns. So ROR, 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 ROR. Same thing here. ORRO, RRO, RRO. So these are, again, repeating cyclic structures of ethers. But what these crown ethers did, or what they do, is they can be used to trap ions. You can see that with the smaller crown ether here, which is called 12 crown 4, that will solvate a lithium ion. The lithium ion can kind of fit into this pocket, and the positive charge from the lithium attracts the lone pairs from the oxygens, and it kind of binds the lithium into that pocket of the crown ether. Same thing here with sodium and 15 crown 5. Sodium will fit into that pocket, and potassium for 18 crown 6. Potassium will fit into that pocket. Here's a picture of 18 crown 6. You can see how the oxygens, the red atoms here, the pink atoms, are kind of positioned on the inside of that ring, inside of that crown, and that potassium can kind of nestle in between those oxygens. If you look at the electron potential map, you can see that very clearly. We have high electron density on the inside of the ring and very low electron density where the potassium sits in the center. So why was this so important? Why did Charles Peterson get the Nobel Prize 20 years after discovering or inventing crown ethers? Well, it was the kind of the first foray into studying the chemistry of how a guest molecule, in this case the ion, will bind or dock into a host molecule. We call this host-guest chemistry. And today, in modern times, we use host-guest chemistry to model how drugs or pharmaceuticals can bind into an active site of an enzyme and affect the enzyme, whether you increase its potency or stop its functionality. The study of host-guest chemistry helped us understand how a lot of biological processes go, as far as the kind of the lock and key model that you learn about with enzymes, things like that. So understanding it from a simple perspective for crown ethers, being able to sequester ions out of a certain type of solvent, led to much more sophisticated understanding of biological processes. So crown ethers themselves have been used, like I said, to sequester inorganic ions out of water. For example, you've got toxic waste where you've got, say, mercury ions, barium, a lot of these heavy metals that form aqueous ions. You can bind those aqueous ions into an organic crown ether, and what you end up with is a layer where the crown ether is dissolved in the organic layer, the water and everything else is dissolved in the water layer, but the ions get trapped in the organic layer, and so you can separate the organic layer from the water layer, and therefore you have now removed those ions from the water by binding them into this crown ether. You can also go the other direction. You can help dissolve inorganic ions into organic liquids. If you want to try to dissolve potassium ion into an organic liquid like hexane, it's not going to dissolve. If you try to make, say, sodium chloride dissolve in oil, it's not going to happen. But if you instead put sodium ions into a crown ether and then dissolve the crown ether into your organic liquid, like your oil or your hexane, the sodium will eventually, at some point, perhaps pop out of the crown ether and it will be stuck in the organic liquid. So, two things: you can use it to put ions into organic liquids, or you can use them to remove the ions from aqueous solutions. We've briefly encountered naming for ethers. There are two systems of nomenclature that are commonly used for ethers. The first is a common system. The other is, of course, the IUPAC system. And as it might not surprise you, the IUPAC is a lot more systematic and more flexible. The common system is easier, but breaks down when you encounter more complicated structures. So the common name system, we will call it alkyl-alkyl ether. We've seen that on the previous slide. We saw this molecule, for example, we would call this propyl ethyl ether because it's got a propyl group on one side of the O and an ethyl group on the other side of the O. So it's an ether with a propyl and an ethyl. We will typically put the more complex alkyl group first. So propyl will come before ethyl. You'll notice back here, they didn't do that. They put methyl first and then phenyl. That is alphabetical. So they went alphabetical here, methyl first and then phenyl second. You would be okay to put the complex alkyl first. So propyl first, then ethyl first. You could go alphabetical, so you say ethyl propyl ether, that would be fine. But technically speaking, methyl ethyl ether would be technically incorrect. If you've got a methyl group on one side and an ethyl on the other, you would call it ethyl methyl ether because that puts the more complex substituent first and the alphabetical first. So methyl ethyl ether is wrong under both systems, under both prioritizing systems. The IUPAC system, however, names it as an alkoxy substituent of the longest carbon chain. So IUPAC, we would call it alkoxy alkane. Example here, the longest carbon chain is 3 carbons, 1, 2, 3. So this is a propane, and then the substituent in green is an ethoxy group. It's an ethyl with an O minus, basically. So ethoxy propane, and specifically the ethoxy group is on the 1 carbon of the propane. So either way you want to name them is fine. You will see, however, that once your substituents start getting really long and start getting complicated branches with perhaps other substituents off of those branches, the common name gets very difficult, because it can be very difficult to name, say, an 8 carbon chain with a bunch of different branches. It's much easier to make it that 8 carbon chain the root and just name this OR group as a substituent off of that long chain. Epoxides, we've seen before, are 3-membered cyclic ethers. Here I want to show you how to name epoxides. We saw taking a double bond in alkene, reacting with a peroxy acid like peroxybenzoic acid. MCPBA is metachloroperoxybenzoic acid. And the result is that you get that epoxide formed between the 2 carbons involved in the double bond. You lose the double bond in order to make that epoxide, and the peroxy acid is converted back into a typical carboxylic acid. The way you name epoxides is as the oxide of the alkene from which it could be formed. So this is ethylene. This molecule is ethylene, or ethene. You could also call it ethene, would be the IUPAC name. The oxide of that would be ethylene oxide, or ethene oxide. So this is the oxide of ethylene. You could also name it as an epoxy substituent, where you have the numbers indicating which carbons the oxygen are between. So this is 1,2-epoxy cyclohexane. There is an epoxy group between the 1 and the 2 carbon. And specifically, they're saying this is trans because there's a methyl on this as well. And you see that the epoxy group is up and the methyl is down. So the relationship between the epoxy and the methyl would be trans. The one's up and one is down. You could also use R and S to designate that. Here, this is a cis epoxy. Here's hexane. It's a 6-carbon chain. 1, 2, 3, 4, 5, 6. The epoxy group is between carbons 2 and 3. So that's 2, 3 epoxy. Notice that we've got a methoxy group here. This is another ether, methyl OR. So this ROR. Notice that it's much easier to name this as a methoxy substituent rather than calling this methyl ether with something other, this gigantic group over here, as the other half of the ether. So this should be 2, 3 epoxy, 4 methoxyhexane. Here's our methoxy group on the 4. But notice that the geometry of this is cis. You can see that the 2 hydrogens here are both pointing up, and that this R group, the methyl over here, and this R group, the chain over here, these are down. So that would be a cis geometry. This would be a trans geometry. There are other cyclic ethers that go beyond the 3-membered cyclic ether. We have 4-membered cyclic ethers, which are called oxytanes, where the oxygen is numbered as the first member of that 4-membered ring. We have oxolanes, which are 5-membered cyclic ethers, again, where the oxygen gets the number 1 designation of the 5-membered ring. And oxanes are 6-membered cyclic ethers, again, where the oxygen gets the 1 designation of that 6-membered ring. You can also have dioxanes, which are a common class of molecules. This is a 1,4-dioxane because the oxygens are on the 1 and the 4. This is a 1,3-dioxane. This would be named 4-methyl 1,3-dioxane. You name the 1,3-dioxane as the parent or the root, and the 1 and the 3 are the oxygens, and the methyl would then be on the 4th carbon. Furan is a special type of cyclic ether. We've encountered furan before in that it is an aromatic molecule. Here's pyran. Pyran is not aromatic, but it is still another commonly seen type of cyclic ether. It's a conjugated system. It's just not fully cyclic, so it's not aromatic. But that's pyran and furan, in case you ever encounter those names. That's what those are referring to. Again, the oxygen is the 1 in the designation of these positions on the ring. So this would be 3-methoxyfuran. This would be a 4-methylpyran. Again, this OCH3 is a methoxy group. And then tetrahydrofuran, we've seen THF before. It's basically furan where we've added 4 hydrogens by hydrogenating the 2 alkenes. So that becomes tetrahydrofuran, which is oxalane. That is the simplest type of oxalane, a 5-membered cyclic ether. So we've got oxetanes, oxalanes, oxanes, and dioxanes. You can also have dioxolanes, where you've got this 5-membered ring where 2 of the members are oxygens. So you can have a 1,3-dioxolane, a 1,2-dioxolane, etc. A specific type of reaction that will create ethers is called the Williamson ether synthesis. And believe it or not, this is one of the first reactions that we ever saw. This is a standard canonical SN2 reaction where we take an alkoxide, an RO minus, and react it with an alkyl halide, an RX, and the alkoxide O minus is going to attack the R that has the halogen. It's going to displace the halogen as a leaving group, and we're going to make an ether. If you go back and review our SN2 chapter, I mentioned that when we do these SN2 reactions, we're making ethers, ROR. That is technically called a Williamson ether synthesis reaction. Here's an example. We'll take cyclohexanol, our cyclohexane alcohol, use sodium. Remember what sodium is going to do? That's going to deprotonate the H and make the cyclohexanol into the cyclohexyl alkoxide. Then we have an alkyl group with a leaving group. In this case, it's a tosylate, the OTS. It could be a halogen, of course, like an iodide. But in this case, we have an OTS as our leaving group. The oxygen from our alkoxide nucleophile will attack the carbon bearing the tosylate, displace the tosylate, and we'll make our ether, ROR. In this case, it's a cyclohexyl ethyl ether. The more complex group is a cyclohexane, so it's a cyclohexyl substituent, and then ethyl on the other side. If you want to name this as the IUPAC system, it's a cyclohexane with an ethoxy group, so ethoxy cyclohexane. Here's a pentanol, a 2-pentanol with a 3,3-dimethyl. Again, we'll use sodium, or in this case, they're using NaH, to remove the acidic hydrogen, make our alkoxide, or O minus. Then our methyl iodide is our alkyl halide. The O minus will attack the methyl, displace the iodide, again in SN2 fashion. Now we've made an ether. It's a methyl ether with this big group on the other side. Now, notice how it's difficult to name this using the common alkyl ether nomenclature system. You've got methyl on one side, that's easy. But then what would we call this? It's like a pentyl with a 3,3-dimethyl. It's hard to name that as a substituent. It's much easier to name it as a 5-carbon chain, a pentane, with a 3,3-dimethyl and a 2-methoxy. That OCH3 again is a methoxy group. We've also seen alkoxymercuration demercuration that was similar to oxymercuration demercuration, but instead of using water to get an alcohol, we use an alcohol to get an ether. So go back and look at that if you remember. That was from the first chapter of reactions of alkenes. You can also cleave ethers, which is essentially the reverse of the Williamson ether synthesis. And you typically do this using hydrobromic acid or hydroiodic acid. Here's the mechanism. If we have our ether, ROR or ROR prime, we will first protonate our ether. So our ether oxygen will protonate from the H, displace the Br. That gets us our protonated ether. That gives us a good leaving group. This ROH is an alcohol. That's a stable molecule. That's a leaving group. What happens next is the bromide that we just displaced comes back and attacks one of the R groups and displaces the alcohol, in this case R prime OH. That gets us ROH and RBr. If you go back and look at the Williamson ether synthesis, here was our ROH. ROH could be deprotonated to be RO minus. So our alcohol, and then an alkyl halide, RBr or RI, or if it's a tosylate for a leaving group, R-tosyl. So the cleavage of the ethers gives you the products that you could start with to make the Williamson ether synthesis in the forward direction. So you can always reverse the Williamson ether synthesis by adding a little bit of hydrobromic acid. The sulfur analog to ethers are called sulfides or thioethers. We'll see a lot in chemistry. Thio means sulfur. So thioethers are sulfur analogs of ethers. They're also called sulfides sometimes. These are smelly compounds. DMS, which is a byproduct of the Sworn oxidation, is a thioether, dimethyl sulfide. This is also the reducing agent that we use in the second half of ozonolysis, DMS. But remember, we said that the kind of fun thing, or I guess you could call it fun, the interesting aspect of the Sworn oxidation is that your product is dimethyl sulfide. You can smell when your oxidation is done. Here's phenyl methyl sulfide, again, putting the methyl first over the phenyl because it's alphabetized, or putting the phenyl before the methyl because it's the more complicated group. Phenyl methyl sulfide is the same as phenyl methyl ether, except that instead of an O, you've got an S. Instead of naming it as alkoxy substituents, for example, naming this as an ethoxy group, if that was an oxygen, we call it ethyl thio. So this would just be named the same way. It's a 2-methyl-2-pentene. Here's our 2-pentene with a 2-methyl, and then it's got a 4-ethyl thio, an ethyl thio group on the 4 carbon. So we're using alkyl thio instead of alkoxy, but it's the same pattern that we use for oxygen. Sulfur is below oxygen on the periodic table, so it has very similar reactivity and bonding trends. It will make 2 bonds like oxygen will. If it's got 1 bond and 3 lone pairs, it's got a negative charge. That makes it a nucleophile. So this ethane thiolate nucleophile, we could use it to attack, say, a bromopropane. That would be an SN2 reaction. Our nucleophile would attack the carbon with the leaving group, displace the leaving group, and we make our bond. In this case, we're making a thioether. So you could call that ethyl propyl sulfide. Again, here they're putting alphabetical ethyl before propyl. You could put propyl before ethyl because it's more complicated. Propyl, a more complex substituent than ethyl. And then sulfide instead of ether, ethyl propyl sulfide. Made the same way, it's just the sulfur analog of the Williamson ether synthesis. Just a reminder, we have done 2 methods for synthesizing epoxides. We mentioned using MCPBA, a peroxy acid. That was what we saw earlier in this lecture, as well as the second lecture of alkenes. We also talked about base catalyzed cyclizations of halohydrons. We made halohydrons which had the X and OH group on vicinal carbons, and they were always anti to one another, which means that if you remove the hydrogen from the oxygen, say deprotonate the oxygen with a base, you get the alkoxide, and that could displace the leaving group X from the backside. That is kind of like a cyclic Williamson ether synthesis. You have an RX and you have an alkoxide, and the alkoxide displaces the halogen leaving group from the backside in SN2 fashion. That gets you a cyclic product, a cyclic ether. So this is like a cyclic Williamson ether synthesis. We've seen this before. This is nothing new. But again, since now we are in the chapters of epoxides and ethers, I wanted to show you this separately. Again, here's the mechanism for formation of the halohydron. You can make the chloronium ion or the halonium ion from one face of the alkene by adding the alkene to our halogen. But then instead of the halide opening the halonium ion, the water opens the halonium ion. It's going to always open it from the backside in an SN2 fashion. That ends up with our OH group on one face and the chlorine or halogen group on the other face. They will always be trans. You can deprotonate the alcohol to make the alkoxide. That will be able to attack from the backside and displace the halogen from the other face. That gets us our epoxide. And lastly, we talked about ring opening the epoxides. One utility of the epoxide was that it was a good electrophile. The ring, being fairly strained, would like to open up. And so we can open it up under acidic conditions or basic conditions. And the rule was that under acidic conditions, the nucleophile always attacked from the more substituted side of the epoxide. And under basic conditions, the nucleophile always attacked from the less substituted side of the epoxide. So under basic conditions, we're always going to attack the less substituted side, and it's going to go from the back side. So our hydroxide would attack this carbon right here to give us the OH down on that carbon and leave us with the O up on the other carbon. Or under acidic conditions, the water is going to attack the more substituted position. That's going to attack the carbon with the methyl group and invert that stereocenter because this is SN2 displacement. So the O would be on the bottom side of that carbon and it would leave us with the O on the top side of the other carbon. Depending on what enantiomer you start with the epoxide up or the epoxide down, will determine which reagents you need to get to which enantiomer of the product. So again, I've shown you this before. I just wanted to include this in this brief lecture to remind you about how epoxides work in the context of ethers. And that is all for lecture 3. So a brief workshop on this material is in Stramanis Chem Activity 20. Other than that, you can find information on ethers and epoxides in the alkene chapter, which was chapter 8, as well as the SN2 chapter, which was chapter 6 in Wade.